This slidecast will demonstrate problem solving with recursion. There's a famous problem in computer science known as the Towers of Hanoi, and it illustrates recursion. The problem is to move the three disks to a different peg, maintaining their order so that the largest disk is on the bottom, the smallest on the top, etc. And the rules are that you can only have the top disk on a peg can be moved to another peg. So we can't reach onto a peg and take two at a time. And a larger disk cannot be placed on top of a smaller disk. So the inputs to the problem are the number of disks, an integer, the letter of a starting peg, L, M, or R, a letter of a destination peg, L, M, or R. It has to be different from the starting peg, and a letter of a temporary peg, L, M, or R, and it has to be different from the starting and destination peg. So three pegs, three different purposes, and the output of the problem is a list of moves. Now a solution to the three-disk problem, to move three disks from peg L to peg R, we'll move the top two disks from peg L to peg M, move the bottom disk from peg L to peg R, and then move the top two disks from peg M to peg R. So that's three steps, and we'd have to do steps 1 and 3 in a way that doesn't violate the rules that we established earlier. Now a solution to the two-disk problem is to move two disks from peg M to peg R. And the solution to that is to move the top disk from peg M to peg L, move the bottom disk from peg M to peg R, and then move the top disk from peg L to peg R. A solution to the four-disk problem, to move the four disks from pegs L to R, would be first to move the top three disks from peg L to peg M, then move the bottom disk from peg L to peg R, and move the top three disks from peg M to peg R. Now here's a recursive algorithm for an n-disk problem, to move n disks from the starting peg to the destination peg. Now we have a base case, which is if n equals 1, we can simply move disk 1, the smallest disk, from the starting peg to the destination peg. Otherwise, here's our recursive definition. We move the top n-1 disks from the starting peg to the temporary peg, and we move the disk n, the disk at the bottom, from the starting peg to the destination peg, and then we move the top n-1 disks from the temporary peg to the destination peg. Now our recursive function showMoves will display the solution as a list of moves. And for the two-disk problem shown earlier, here's the list of moves. We would move disk 1 from peg M to peg L, disk 2 from peg M to peg R, and disk 1 from peg L to peg R. And the function showMoves must have the number of disks, the starting peg, the destination peg, and the temporary peg as its parameters. So here's the C++ function signature for that showMoves function with the parameters we just described. And we'll build a string containing all of the moves for a game with n disks on the starting peg to move to the destination peg, and we use the temp peg for temporary storage. Here's the recursive function in C++. So our showMove functions, the precondition is that we have to have three different pegs. The postcondition is the list of moves to solve the problem for the n disks. And we have an n parameter, the number of disks, the start peg, the destination peg, and the temporary peg. We return a string of all the required moves. And it's a surprisingly simple function. If n is equal to 1, then we move disk 1 from peg start peg to peg destination peg. Otherwise, we have a recursive step to show moves of moving n-1 disks from the start peg to the temporary start peg to the temporary peg using the destination peg as a temporary peg. Okay, so the result of this move is to move all the n-1 disks to the temporary peg. Then we'll output the single move to move disk n from the starting peg to the destination peg. And then we have another recursive call to remove the n-1 disks from the temporary peg to the destination peg, and we'll use our start peg for temporary storage. The author provides you a program for testing, and you can input the number of disks, you can enter the start, destination, and temporary peg, and then it will go ahead and call show moves to solve the problem. And I encourage you to go get that program and run it and see how it works. Another problem is counting cells in a blob. So consider how we might process an image that's a two-dimensional vector of color values. And this information could come from X-rays, MRI, satellite imagery, these kinds of images. And the goal is to determine the size of any area in the image that is abnormal because of its color values. Now, given a two-dimensional grid of cells, every cell would have either a normal background color or a secondary color, which could indicate the presence of an abnormality. And a blob is a collection of contiguous abnormal cells. So a user will enter the XY coordinates of a cell in the blob, and the program will determine the count of all cells in that blob. So the inputs are a two-dimensional grid of cells and the position of a cell in the blob, and the output would be the count of cells in that blob. Here's an algorithm for a function count cells. So if the cell at grid position RC is outside the grid dimensions, the result's 0. Or if the color is not abnormal, then the result is 0. Otherwise, we'll set the color of the cell to a temporary color, and the result will be 1 plus the number of cells in each blob that includes a nearest neighbor. So here's our C++ program. We keep track of a background, abnormal, and then a temporary color. And the size of our array is 5 by 5. And here's our count cells function. And the precondition is that abnormal cells are the abnormal color and everything else is the background color. And the post condition is that all cells in the blob are in the temporary color. Now we take inputs R and C are a row and a column of the blob. So R and C together give us an index to a single element in the array. And we return the number of cells in the blob that contains grid RC. So let's look at the code in the function. If R is less than 0 or greater than or equal to row size, or C is less than 0 or greater than or equal to the column size, then we return a 0. So this is the case where we give an index number that's outside the boundaries of the array. If the color is not abnormal, then it's not part of a blob and we return 0. Otherwise, we set the color to temporary at this grid cell's location, and we return 1 plus a recursive call. Here are 4 recursive calls where we, in fact, I'm sorry, there's 8 recursive calls. So, and notice we have an R-1, C-1, R-1, C, R-1, C+1, etc. If you go and look here, you'll see that these indexes correspond to the 8 neighbors for a location in the grid. What we mean by that, let's back up to an array. So if I consider this blue cell in this location, its 8 neighbors are all at this positions 1, 2, 3, 4, 5, 6, 7, 8. And go back and look at the code, and you'll see that if this is at row row R, so let's say row 0, 1, row 2, and column 0, 1, 2, 3. So if this is row 2, column 3, then we're essentially, we count this as abnormal, and we'll add to it the result of a recursive call pointing to each of its 8 nearest neighbors. And all these in white, let's say that white is the background color, those should all add up to 0, but this, we should include this count and then all of this cell's neighbors. And the reason we change, once we count a cell, we change its background to temporary so that we won't count that again when we consider a nearby cell and try to count its neighbors that have an abnormal color. So study this expression and see how what this is basically doing is it's adding together 1 plus the count returned from all of its neighbors. Now for testing, we have this count cells function, and then here in a main routine we declare an array and set its cells to either background or abnormal, and then we can enter a row or a column and display the results. And we could come here and we could modify this and try some different test cases. Say when everything's background or everything's abnormal and other combinations. Now in testing we can verify that the code works for the following cases. The starting cell is on the edge of the grid, no neighboring abnormal cells, a cell whose only abnormal neighbor cells are diagonally connected. A bullseye is a starting cell whose neighbors are all normal, but their neighbors are abnormal. A starting cell that's normal, a grid that contains all abnormal cells, all normal cells. And that brings us to the end of this slidecast.